let's see. We've come through chapter 2, then into 3, which is nothing more than what was really in 2, except you sum the forces in the x, the y, and then the z, and you set them equal to 0. And what I'm going to do is I'm going to start bouncing a little bit, because all the stuff that occurred in 2, as far as finding your vectors and the base vectors, the unit vectors, all occur here, and they all occur here. So what I'm going to do is go ahead in chapter 4 and start covering in chapter 4. And then I'm going to start bouncing back and forth between these two working problems, because sometimes the pictures are the same. So with that in mind, let me go ahead and start into chapter 4. And what you'll see is something very, very similar. And the only difference is he starts working on moments. And he starts with the description right here of what a moment is. And in a way, if you look at these 3, it sort of makes sense. If you're attempting to tighten a bolt and you grab a wrench like this blue thing right there and start pushing this way, of course, you're going to tighten it. But if you start pulling the wrench this way, nothing's going to happen. You're not going to tighten the bolt. So what he's showing here is he's showing that there's a component of the force here. He's showing that in this particular case, if I were able to break it apart into its components, say, trying to make the little, so essentially what you've got is a force that's perpendicular, and then a force that is essentially not perpendicular but parallel to the wrench. And this one doesn't do anything for you. That's not helping you tighten it or anything. This one is. This one is the one that's helping you create the torque. So there's got to be a relationship where it ignores this component and pays all of the attention to that component. And it turns out, let me erase all this stuff now. Turns out that, of course, is what's happening in this chapter. So the first thing he does, he moves along, he starts talking about this magnitude of the moment. Okay, so there are statics and dynamics and some of the other things you've seen. There's really not a delineation between a torque and a moment. You buy a torque wrench, essentially, in the store. They just call it a torque wrench because you're producing a torque. I haven't ever seen anybody buy a moment wrench. So in essence, when you see those are kind of interchangeable. The only thing I've ever seen is in statics books, it tends to be such that if it's a static problem, they'll call it a moment. If it's a dynamic, sometimes they call it a torque. But it's both the same thing. So, but in essence, all it is the perpendicular distance times the d that it's away times the force, and that's the moment. I mean, it makes sense if you're out there doing your tire. Say this is the bolt for the tire, and one of your bolts is really messed up. I've seen people take a little torque wrench and go get a piece of plumbing pipe and stick over it. And if you stick that piece of plumbing pipe over the wrench and start moving it that way, you get a huge moment arm. So this D goes like crazy, because you really can't, I mean, there's a limit. Each human has a different amount that they can put on there as far as a force goes. What you can adjust is the D. And so essentially that that is what's happening. So he goes through this. he looks at things like this, if what you'll first notice is that he comes up and starts breaking away sines and cosines. You'll see these type things. Now, what actually happens next is he comes out of section 4.1 into 4.2, and he introduces the cross product. And he's not just randomly putting that section in here. There's a reason you're, what happens if I hit that? Uh-oh. Okay. Do that. Oh, okay. So I didn't know these things were linked like that. Turns out there's a reason this cross product works. And he describes a little bit of it, and then he uses his right-hand rule. So essentially, if you have a vector A and you vector B, you use your right hand to figure out the direction. You take A cross B. Now, if it's B cross A, you got to take the first vector crossed into the second vector. But it turns out that the magnitude ends up being the torque. Now, he goes through some of the laws of operations here. One is that, you know, they're opposite to each other. If you take A, rotate it into B, you get your thumb going one way. If you take B, rotating it into A, it goes the other direction. And then he's got these things, which you can memorize if you want to, or you can think about them and draw up the axis. And that is, you know, if you take I, you cross it across to J, and your right hand points to K. For that matter, if I take I cross it to K, so I cross K equals to minus J, your thumb will point that way. So there's little things like that. And he's got the whole set down here if you want to look at them. So here, let me get rid of all this mess now. But he finally, well, then he introduces this. Now, I'm a particular fan of this method because this method is kind of, if you're doing it where you're writing them out, then what you're doing is you're writing out this one, looking at the base vector crossings and recognizing that that's 0, this one's 0, and that one's 0, and you're keeping track of everything. So you're keeping track of the minus signs that occur, the plus signs that occur. When you do it in a determinant form, it's all listed there, and then you can cofactor it out. And he talks a little bit about that cofactor expansion right there. So to me, I always basically take the first vector, lay it in the row, take the second second vector, lay it in the third row, and the IJK on the top row, and just start crossing stuff out. It tends to work really well. Unless you copy down things incorrectly, there's less chance I've seen over the years of making a mistake using it this way. Okay, then he talks about this, and this is, you know, you've seen this part before where you do the cofactor expansion. The big key here is this, and he should have boxed that. That's what he's shooting for, is that, in fact, if this thing is kicked off, that one doesn't. Turns out this exactly matches that. And you can look at the derivation, the showing up of the sign in there and things like that if you want to. Here, let me see if I can just see if it gets rid of all that. So then he's talking about this principle of transmissibility, which actually he should have done that earlier, but let me just address this with I'll make up a problem and we'll just address something like that. So let's say we had, it always starts this way. Let's say we had a vector goes out here. Let's say this is a wrench. So let's make this a wrench, okay? And I'll say this is 4 long. I'll say this is 3 long. So that makes this whole wrench equal to 5 units. And then what I'll do is I'll do something silly like put a force out here equal to, I don't know, 10J. And I want to find the torque produced by that. So I'm going to just use his formula. If you look back, oh, it disappeared. Well, it was there, but it was the page before. There it is. It's R cross F. So if I want to find the moment is R cross F. So the R is where you want, there's a point in which you want to find the moment about. Go away. So you could call it O. So there has to be a point associated with it. And if you move around and pick another point, there's a different moment about that point. It doesn't make sense to pick any other spot except maybe the bold. So if I list this thing, just go in and do it, leave myself plenty of room, I end up with this. Then my R, I take my first, so what I'm doing is R cross F, take my first R, it looks like I got a 4, looks like I got a 3, looks like I got a nothing. And then I take my second one, my second vector. So I've just got this. So I've got nothing in the X, I got 10 there, and I got nothing in the K. So now I'll just list this thing out. Hang on. Let me write each term. Then I'm going to start interpreting each of these terms. And give me a second. Um, 4, 3, 0, and 10. Now, the first thing that you probably recognize is if I go, how did he do it? Well, I guess I could do it this way. You go here minus that one. How about that for a way to do it? That doesn't give you anything because you got 0 on both those. You go this way, gives you a 0. You come back this way, it gives you a 0. You don't have anything. Let's pay real close attention to this one. So I'm going to write it down. 4, 3, 0, and 10. Well, oh, and a K. So if I look at this thing, I'm gonna write it down now. 4 times 10 minus 0 times 3. So it just becomes 40 if I'm not mistaken. Oops. So what is transmissibility? Let's suppose that here, and I will try to, if I do this, I'll just try to copy it. I'm going to copy the problem and go down to the bottom, put the thing down in here some. So let's suppose that I take this force, I look at a line, whoops. I look at a line in the direction of this force. And I decide I'm going to, instead of putting it right up here, I decide I'm going to put it right down here. And I'm going to put the same force, it has to be the same force. So in essence, what I'm saying is, imagine, if you will, for a minute, instead of this being a wrench, maybe I should do this to make it, to remove that question in your mind, you know, get all the blue off here. This time, the wrench is a big blob that goes down like this. It's now a funny looking wrench. So now you have a blue wrench, and you decide to go down here at this point and push it like that. So now you're not putting it here, you're putting it here. F is equal to 10J. And I'll say now that this distance down here, just call it D. So if you grab this part, I'm going to go back to this part and look at it. K times, it's no longer at 3, it's at 4 minus D or some distance D, 10. Now, if you look at this thing, it becomes 4 times 10 minus, well, I'll say minus D, minus D times 0. So what this means is anywhere along this line, I can put this force and it won't change the moment. So if you look back at his book, I guess it was the next page. No, it was the same page. He's talking about this line of action, the principle of transmissibility. So essentially what he's saying is, I don't care if you have an R, R1, R2, those are all the same because it doesn't matter where you put the load as long as it's along the line of action. So you can do the math all you want, as many times as you want, you'll find the same thing. So you can take the force, and so for example, let me give you a case that might show up. So somebody says, put a moment, okay, so I have an object that's sitting here, I'm just making yellow objects. I'll make a blob. Here we go. We got a blob, and want to find, say this is connected here. You want to find the moment about this point A. And then somebody tells you it's out here, and I'm going at some funny angle. Then here, I didn't do a good job. Let me move this to maybe over here. Here, and get rid of this thing. So the question is what is this? So let's say it's put right here. So then I just move it backwards or forwards. And then I say, well, I just want to find the perpendicular distance there. So it's true there might be some other distance, but say this is D and this is F. So even though it's applied out here, the moment is still just dF, D times F. Now, you can go in and do the math like I did above here, and you'll find that that always is the case. So if you see a point applied or force applied at some weird point out here, you can move it back along that line. And if you have it convenient, maybe you had the geometry such that you could tell that that's just 10 right off, but this is some weird distance. Say this is D is equal, D1 is equal to, you know, some weird number or something. But in fact, you could look at the geometry and tell that's just 10. Then just move it along the line until it's perpendicular to it. Okay, where'd the book go? There we go. So this principle, recognizing that at times will be kind of helpful. Okay, I think I put some spots. No, there is a, what is going on here? Oh, that's part of the, okay, I was looking at that red dot thinking that that was part of this pen thing, but it's not. So then he comes up with the general form, okay? So I maybe jumped the gun. He's come up with this. Now he did box this, and that's, yeah. So here, this is another reason I rely heavily on this, is that there may be a complex geometry that is, you know, very strange like this. And at first glance, it may overwhelm your mind until you recognize that, hey, do I know Rx? And you find Rx, which is this distance. So you look at your geometry, you're trying to find that. Then once you find that, you begin to say, well, what's Ry? And then it's kind of hard to see this, But ry is, let me see if I can get it around here. Ry is this vector right here. And then you find rz, which that's easy to wrap around. That's this. Once you have that, he's wanting you to find the moment about that point. Then somewhere there might be a complex geometry in order to find fx, fy, and fc. So what you've done is if you can find all 6 of those components, you're free and clear. All you do is put it in this matrix, take the determinant, and you're good. And so here, let's take a look at a particular. Here you will see why you never, ever escape chapter 2. Take a look at this. So he's got this tractor out here. What does he do? First thing he does, he says, I got to find the base vector out there to it. Well, before I do that, what is he doing first? He takes and finds his RA. He finds his RB. Now me, I would sit there and say, well, I have a vector that points to here. That's B. This is A. So I'm looking for the vector, which points to B, originating from A, is equal to RB minus RA. Now, see, that's using the mindset from dynamics that you'll eventually face. So what do? You take this vector, subtract that vector, which that's why you get the minus 12. And then that is, in fact, your vector that points to B originating from A. Then, of course, you take the magnitude of it and divide it out so that you have a unit vector. So it's of length 1. And in fact, let's see, wait a minute, move this over to the side. Okay, and then he's defining this to be 2 kilonewtons. So he multiplies his unit vector times 2, and he gets this. If you look at the size of this vector, you know, this F should be length of 2 because he made it that way. The next key is, okay, I need to find the moment. Well, first of all, determine the moment produced by the force about point O expressed as a Cartesian vector. So let's do something interesting here now. What he has done, this to me is exceedingly annoying. But you'll see me be annoyed a little bit occasionally. So he's wanting you to find, he is actually looking for, well, this problem is not as annoying as some of the others, so I'll find the more annoying ones later. He's going in and finding O. He wants to find the moment about there. He grabs RA, which he's already got. He lists it. Then he goes back to his 3 components here of the force and just lists them. Now, well, I guess I shouldn't be that annoyed. Wow, they got gypped. They paid good money. And they're leaving already. Why don't y'all talk to them and get them to just give you half their tuition? You think they would? I say that in dynamics and everybody laughs. You guys are not. You guys are confused. Okay, so he takes the I. And he's taking this one times that one. And this one times that one. Then he takes the J, okay, and this is getting, okay, this is getting bad now. Takes the J, so he's taking this one. He's got that minus that. And then he ends up with the K. And then, of course, and this thing is very annoying because it does not move with the page. So he ends up with this. He wanted to know, okay, I'm just checking to make sure what he's asking. He wants to know about point O. This part, the last part is a little bit annoying. And me, the way I do it is I don't. Well, he did a nice job here too about listing the moment. One of the things I look at is, I tend to think and have seen that this part right here causes a little bit of confusion. However, if you stare at it long enough, it makes sense. However, often you may not have time to stare at it that long. If someone is asking you to find a moment about about point O, and there's a force out here somewhere, I don't care what other geometry it is. If you find the origination of the force and the R that goes out to it, just cross those. Don't try to interpret oddball things like this. And so maybe what I'll do is do enough of these that you see that kind of mentality kind of always works. But if you want to stare at it and read it and think about it, it may make sense to you. But I would say be careful a little bit. Okay, so here's another case. He says two forces act on the rod, determine the resultant moment they create about the flange at point O. So he's immediately identifying what he wants to find the moment about. So what does he do first? Now, this is what I would do. I would basically find my vector, and I would say my total moment is going to be RA crossed with F1, because that vector drew it all the way to the point where that load sat. And then I'd add to it RB crossed with F2. And that's it. So you're drawing a vector that said, what am I taking the moment about? Let me draw a vector from there to wherever somebody drew that load to sit. That's it. Figure this out, and I can figure that out. I'm not going to translate or move things along the line of action. So, and he did. He gave you that. He gave you that. Now, I can tell you, you can go out and find RA pretty easy. It looks to me like it goes 5 out there in the J, and you're done. Now, the RB is a little bit different. RB, you got to go, and let's do the I first. 4I, because it went out that far. It went out 5J, went out that far to B, and then it went down to K. And you'll see that these are what he got right there. Now me, I don't know what he does, but I would just list those things. And thank goodness that's what he does. Takes the RA, just list it. RB, F1, that was just given to you. 60, 40, and 20. And then the RB, which is this one, 4, 5, and -2. And then 80, 40, 30. And then often you can do stuff like that just in your calculator. Let's go ahead. They installed MATLAB. So I have that. Let me show you this kind of a cool thing here that makes your life easy too. Let's just take and do these. Okay, so RA is equal to, and I'm going to do them in vector form, which is 0, 5, and nothing. And it lists it there. I think that's okay. RB is equal to 4, 5, and -2. 4, 5, -2. Now my vector F1 -60. Did I put the bracket? I did not put the bracket. -60. I'm getting it from down here. I'm just reading them off right there. -60, and then 40, and then 20. Did I do that right? And then F2 is equal to 80. Did I put the equal? Yeah, 80, 40, and minus 30. I got 4 vectors listed here. That's what I meant to say. So I got 4 vectors, F1, F2, RA, RB. So let me just figure out what he says. Okay, so I'm going to cross RA. He's trying to get, look, he's trying to give me help. RA and F1. And then I'm going to add to it the cross, oh, didn't spell that right. RB with F2. And there's the answer. And what you'd find out is I can't go down. For some reason, it won't go down. Oh, wait. Okay, so you see right here, that in fact is what he has. Oh, look, it doesn't. Okay. I guess this is window to window. So using this, I mean, I don't know, maybe do your calculators have this ability to do cross products and stuff? Oh, they don't. So this is, to me, that's a good help if you're doing a problem. You could break out either MATLAB or Octave, or there's another one, Scilab. They all have this cross thing in them. Octave and MATLAB are the simplest to me. So now let me get all this garbage off of here. Okay, so, okay, and what he does throughout chapter 4 is he kind of it always works if you draw the vector from where he's asking the moment about to the point of the application of the load and cross them. It always works. Now he's looking for very specifics. So in this particular case, he's doing, where you can you look at the perpendicular distance D. If I had X and Y, I could do some geometry and find D and then multiply times F. Okay, that's fine. There's nothing wrong with that. There's a lot of other sub cases that you could work off of. Here he gives you a funny 75-degree line and a 30-degree line, and then there's a 45-degree line. And what does he determine the moment of the force about O? Now I'm just going to find the vector that goes from here to here, and then come up with my Fx and my Fy, and I'm going to cross them. And what he's doing is he's dropping in there to find the distance. And I'm just like, I don't want to deal with that. So I tend to want to work problems in a way that always works and that I don't have to think too much about. And so this is, here, this one, the solution 2 is more along the lines of what I would do. And in this case, okay, so he does this bar here. He says scalar analysis, that's okay. There's nothing wrong with that if you can see that. Solution 2 is vector analysis. And in that particular case, if I'm seeing this, I'm comfortable there. So you will see me always working with that. It's okay. Either way you want to do it. So let's take one that is, let's just do this 4-1 because that won't take too long, and then we'll go about our business. But what you'll see in here, you'll see that these things, look at 411. 411 is grabbing stuff from chapter 2. Find the base vector going from B to C, multiply times 120, then draw the vector from O to B. So you're going to find your U there and multiply 120 times your U. That'll be your force. And then multiply R crossed with that force. And that's going to be your moment about O. So you can't escape that stuff in chapter 2. And that's one of the reasons I just continue to go, and I'm going to bounce through chapter 4 and then go back and work stuff in chapter 3. But let's do this simple one real quick. And I don't have the little snippet thing up. Okay, so I'll just grab 4.1, and he says, determine, here I'll do a new page. He says, find the moment about point O, and me, this is what I'm going to do. He says about point O, I'm going to draw a vector from here to here. Now, he drew this vector, the application right here, it could have been drawn on this side just as easily. So what I'm going to do is I'm going to say, well, what's the vector? Vector is equal to 5I plus 2J, and it's in meters. So, and then the point of the application load, the value of that load looks to me like it's 4I minus 3J. So the moment's just going to be I, J, K, and I'll grab this one first, 5, 2, and nothing, and then 4 minus 3 and nothing. Okay, so here's what happens in this. I got this column of zeros. It's in a plane, so the only moment can be out of that plane. Because if I do a cofactor expansion, they're still being cheated. Look, I get this minus J, 2 minus 3, 0, 0, and then plus K. This is the only one that ends up with anything. That's supposed to be a 2, not a 3. So you get the moment is just nothing more than K, 5 times minus 3 minus 2 times 4, or that's 8, and this is 15, and they're both minus. What is that value? Calm down. Okay. I don't know why my page. So, and it's supposed to be times K. What is that? 23K. Now, first of all, the minus 23. If you look at it, here's X, here's Y. This is in the plus direction. If you cross I with J, you get K. So that means you take your hand on X, I, whatever, you cross it to J. Then the moment that twist like that coming with your thumb coming at you is a positive. So that means this is saying it's twisted that way. It's twisted opposite. It's twisted into the board. And that makes sense because, if you look at this thing, you get a component right here doing the moment, and you get a little component right there that's not producing the moment at all, where this is that. And so, we can go look at the back of the book. Let's see what 4.1, right? Okay, so if I go four one 460. Did I do that right? What answer did I even get? Uh-oh. Wow, that's terribly done. Uh-oh. You know what I did wrong? What I do wrong? Can y'all see it? What did I do wrong? There you go. How did I mess up? What did I do wrong? Yeah. Yeah. put the wrong thing. The force I've got is 5, not 100. So my answer should be 20 times that, because 20 times 5 gives you 100. So I bet you if I run down here and multiply 23 times, what's 23 times 20? What is 23? Oh gosh, 23 times 20, 460. Oh, I put the wrong force in there. I saw the 4 or 5 and I didn't even pay attention to that 100 newtons right there. So I owe you $1. Where'd the book go? Okay, so that's why I see, he did it totally different. So do y'all see how I messed up? So in fact, this thing should have been, the force should have been, what's 20 times 4? Is that 80? And then 60 J. That's what should have sat in there. Instead, I put this instead of that, which is just a scale. You just take that, multiply it times 20, you get this. But for some reason, that just passed over my head, and I didn't even pay any attention to it. So this number's wrong, that number's wrong, and those two are wrong, which that doesn't matter. But this should be times 20. That should be times 20, which eventually ended up making this to be 460. Now the question is, did he say minus? Oh, he said this. So he's saying like this. So rotating with your thumb into the page. And if you look at it, that makes sense because the thumb out of the page is positive. So the thumb into the page is negative. So in fact, that, I was okay. That's right. So except the fact that I just failed to look at that, It happens. So I don't want to cheat you. 5 minutes. So let's see what, here, hang on, let me get rid of that thing. Okay, we started in there, we got, okay, so what he does, okay, he's in here, we're doing this, then he gives you a set of problems. They look physically different, but they all come down to the same mathematics. Okay, what does he do? He calls these problems. Then he makes them interesting by doing things like this to him. So what we'll do is we'll come in and do some of these next time, and we'll see that, as long as you can sort of deduce what's happening, it pretty much works out. Okay, so then the next thing is, what does he do? Okay, moment about a specified axis. This goes along with the concept that we talked about the rotation about the door, or things like that. So for example, and I don't do it the way he does it. I basically take and find the moment vector and then go ahead and dot it. I dot it after the fact. He does it before the fact. So in fact, for example, if you look at this, the guy has a single tire iron and he's producing a moment. And in fact, he's producing a moment, if you look at it, he's producing a moment like in that direction. But that moment, who cares? This is the moment that you care about, because this is the moment that's tightening or loosening the bolt. Now, if you have one of those ones that you're grabbing on both things and doing like that, that's called a couple. That's like another section or two. So you can actually, so if you draw a vector from here to the point of the application of the load, R, okay, let me see if I can, R, which is out here. Oh, R cross F. Okay, so his R goes here, his F goes up. I thought he was pushing down. I mean, me, I would push down because that's a lot less on you. So I would do, and wouldn't hurt your back. Cross that, and you get a vector coming out here, out in this plane. That's what's happening to you when you tighten your tire. So what? That's fine. You're wasting this part of the moment. That's not producing anything. In fact, that part of the moment is actually possibly bending your bolt up. This part of the moment that's doing this way is helping you either, I don't know whether he's tightening it or loosening it. Usually it's like that to tighten it, so he must be trying to loosen it. So he's trying to get them out, but this part is not doing anything. That part of the moment is useless. So what do? You take your moment. So you say, this is different what I would do. I would come up with that moment. So I would come up with that, and I'd get a number. I'd say, 10I plus 10J plus 0K, and I'd get a number. And then I would dot it with this little unit vector. It comes out here. Well, this little unit vector in this case is just that, the J. So all you're doing is you're pulling the J component of that vector. So he has this, he tries to do it in all one swoop, and in the problems he does do it in all one swoop. I don't. I always break it into two parts, just because I feel more comfortable that way. I'm not if you feel comfortable doing that, hey, that's fine. But what you're going to get out of that is just a scalar, and that's where I like to keep track of all that. Here's another case. The tire case is a really good case, but this case is a case in which if, say, there was some sort of, so say this is a metal strap, and this one, say, had a metal strap with a piece of rubber on it to keep the thing from falling over, then you kind of want to know what type of moment you're having to resist. Otherwise, this thing the whole, whatever this object is, will start rotating. So what does he do? He finds the base vector around that thing, and he can find out the moment along this AB so that you could put that piece of rubber down there and tighten the bolts down so it could resist that moment. Okay, so what does he do? First thing he does, to me, I would say I'd draw a vector from here to here. I'd cross that with this, and I'd say, I got a moment. Then I would say, oh, let me find this vector runs out this way, and I'll dot the moment with it, and I'll find the moment in that direction. And that's just me. Now, what he does is he goes ahead and puts them all together. He finds the base vector running out B, so he finds the distance along B. He divides by its length, gets him a base vector or a unit vector drawn out here. He puts it in the first row. Second thing, he's going to try to draw a vector from here to here. That should be 0.6, 0.3. Okay, now, this is cheating. This is just plain flat cheating. He does not include the 0.3. What you find out is, and we'll address this next time, it doesn't matter what you put there anyway. But that is just obnoxious and wrong in this case, because you're learning the material, you need to have it complete. And then the force is just straight up right there. So I despise the fact that actually it's supposed to go right here. I despise that fact that it's not put in there. I think that's just dead flat wrong. That is not RD. So we'll look at this one when we come back in here. Oh, you got two more minutes than you. Of course, I started 2 minutes late. So you got your fair dog. So you don't have to leave your cash at the doorstep. You already did that.